A stone is dropped from the top of a building. The stone's displacement in the last second before it hits the ground is 50% of the entire distance it falls. How tall is the building? So over here, I have a list of the four most important, or the four basic kinematic equations that we can use to solve problems of this type. So to start, I'm going to use this first equation here, which says that the displacement is equal to the initial velocity times the time plus 1/2 times the acceleration times the time squared. So I'm going to break up this stone's trip from the top of the building into two segments. So let's let the first one be the displacement 1, or delta x1, and let's let the second one be delta x2, or the second displacement. And this first one is going to be referring to the displacement before the last second, or before it falls the 50% of the entire distance. And delta x2 is going to be the last second where it falls 50% of the entire distance. So we can use this to help write some kinematic equations. We are going to set the reference frame to be the positive x-axis downward, as that will prevent some negatives and simplify our calculations. So with that, the displacement, the first part can be represented as 1/2 gt squared, where g is the gravitational acceleration, since we have no initial velocity in our first case, since it's just dropped from the top of the building, not thrown down. So I'm going to let this t be t1, or the time it takes before the last second to reach 50% of the distance. And change in x2 is going to be the initial velocity. I'm going to call this v1, and this is the velocity after it's falling from the first displacement here. So after it falls 50% of the distance, its initial velocity, its velocity will be v1. And we're going to multiply that by t. And this case will be t2, since t2 is the time for the second part of the displacement for the rest of the 50%. And of course, we add 1/2 gt2 squared. And note that t2 is going to be equal to it's going to be equal to 1 second, because the stone's displacement in the last second before it hits is 50% of the entire distance it falls. So we've set change in delta x2 to be this last 50%, and the time it takes is 1 second. So we can simplify this to delta x2 is simply equal to the velocity after it falls the first 50%, plus 1/2 g. So we can simplify that. But we don't know what v1 is yet, so we need to figure out what v1 is. So that's where this equation comes in handy. That says that the final velocity is equal to the initial velocity plus an acceleration times the time. So in this case, our final velocity is going to be v1, because this is the final velocity after the stone falls the first 50% of the distance. And that's equal to the initial velocity, which is 0, because the stone starts from rest, so we can ignore that. Again, there's no initial velocity. So plus the acceleration, which is g, times the time, which is t1. And that is the expression we get from this equation here. So substituting that in, delta x2 becomes g times t1 plus 1/2 g, and we can factor out the g to get g times t1 plus 1/2. And that's our expression for delta x2. And we know that delta x1 must equal delta x2, because delta x2, or the second part of the displacement of the stone, is equal to 50% the entire distance it falls. So delta x1, or the first part of the displacement, must be equal to the other 50% of the distance. So these two must be equal to each other. So we can substitute our values in. Delta x1 becomes 1/2 gt squared, and that is equal to delta x2 which is g times t1 plus 1/2. So I'm going to erase some of this stuff up here to make more space. Again, we're solving for t, for the t1. We're solving for the time it takes for the first part. And we are going to need these equations later on, so I'm going to rewrite them down here. G t1 plus 1/2. And then we can rewrite this up here. So from here, the g's cancel, and we're left with t squared is equal to 2t1 plus 1. I just got rid of the g's, multiplied both sides by 2, and then distributed. And then so we can solve this. We can reorder this into a quadratic equation. Set that equal to 0. And then from here on, we just simply use the quadratic formula, which is simply x equals, or in this case, it's going to be t. Must not forget the subscript. We're dealing with t1. That is equal to minus b, just 2, plus minus the square root of b squared, which is 4, minus 4ac. Just since this is negative, the negatives cancel. This becomes 4 times 1 times 1 divided by 2a. So simply 2 times 1. So this becomes 2 plus minus the square root of 8 divided by 2. And this yields you 2.414 seconds and minus 0.414 seconds. And looking at these two, it becomes obvious that this can be our only choice, because we can't have a negative t1. So this is the only real answer. This is the real time. This is the one that we want, since it's the only possible one out of these two. So we're going to set t1 equal to 2.414 seconds. And now that is what we get after we solve for time. Now the rest of the problem becomes pretty straightforward. The total height, which I'm going to call h, is simply the sum of these two displacements. Since they're each 50%, they must add together to give us the height. So this becomes 1/2 g, I should specify this is t1 squared for change in x, delta x1, plus delta x2, which is g times t1 plus 1/2. And again, we can factor out the g's again to get 1/2 t1 squared plus t1 plus 1/2. And now we can just simply plug our values in. G is 9.8 meters per second squared times 1/2 t1. We calculated to be 2.414 seconds. Square that. Plus 2.414 plus 1/2. And then we're going to multiply that all by 9.8. And if you solve this, you should get that the height is equal to about 57.1 meters. So the building is going to be 57.1 meters. And again, this is if we neglect air resistance. But this is how you would solve this problem here.